Hi, welcome to the final day of the biostatistics training. Today we'll be exploring volcano plots. Um, we've had kind of a pretty rapid introduction to R here. We spent basically a single day on language basics. We looked at doing jitter plots as an alternative to dynamite plots and also box plots, very valuable. Yesterday we looked at MA plots for looking at biases in signals between our cohorts. But today we are proceeding to kind of the classic example of differential gene expression plotting, which is the volcano plot. Are there any questions as we move forward? Feel free to just put your hand up and we'll try to come to it. I'm recording this one on my laptop, so the dead battery of the video camera will not vex us. If the screen starts flickering, I may ask you to just imagine the results, but we'll do our best. So we're going to start, as usual, by loading in the library that we'll use for plotting, ggplot2. Again, if you haven't already run install packages to get ggplot on your computer, you'll need to do that. And we want to read the transcripts. But as we should all recall at this time, you have to tell R where to find that file. So I'm going to change my current directory to the directory that contains these files. It's the proteomics and R biostatistics training. I can do a quick list files to tell me what's in here. I'm in the right place. There's my DF transcripts file down here. So I can now run the read table command that's going to create a data frame object from the DF transcript CSV. It's comma separated as before and grabs the names of each column from the header line. Was everybody able to open that text file and get it loaded into memory? This is good. Okay, great. Let's proceed then. Once again, I don't want to keep the full set of transcripts. I'm going to care just about those that have the gene names on them. So again, that is a big scale down in size when we look at the original table versus the current table. We have both of them have 19 columns. That's unchanged, but we have only 1,047 with gene names specified, and out of 2860 that were in the original file. All good? Okay, so for this next part, we're going to start talking about p-values. Let's start by just asking, how are p-values distributed? All right. This is worth talking about because I think it's something that's not understood. In the sciences, we spend a lot of time looking at significant differences. And the way that we define significant differences is a little different in each context. So we start by computing p-values at the level of individual genes. All good so far, but we need to remember that a p-value, as generated by the software, is telling us about essentially how far we are from random behavior for this individual gene, ignoring the fact that we have all these other genes also in presence. So here we see a very small number of genes that have p-values below 0 and 0.1 that have slightly more than average in that lowest category, but the p-values are spread all the way up to 1. Why is that? The expected behavior of t-testing and p-values, if given 10,000 tests or 20,000 tests or whatever, is to produce values that are uniformly distributed between 0 and 1. So if there's no difference to be found whatsoever, the p-values will still range uniformly from 0 to 1. So the stuff that's really going to get our attention is all down here at the base. But the great majority of our data don't have p-values that are very, very low. Those p-values that are very, very low are those that where you couldn't explain the distribution of the data if they were just coming from random sources with the same means. So it's worth remembering that if you detect p-values in an experiment that are all lumped down close to 0, that's kind of a problem. That's not the expected behavior. Most of the genes we're looking at have no differences in mean. So finding this uniform spread across that space is what we expect. And it's good to check that, because a statistical model that's just giving you all low p-values is problematic. Okay, this is not the only way to do that. You'll sometimes see people using QQ plots and things like that to show the distributions, but this is a quick way to evaluate that. All right, I'm going to close that plot. Okay, so let's come back to our script here. We are going to plot all of the values from lowest to highest. This is an example of nesting functions. So we have the function sort that's going to be used on this vector of p-values. That's going to arrange them, in this case, from lowest to highest. You could set a parameter called descending to true, and then it would sort them from highest to lowest, but you see that's not very different. The value, the vector we give it is not sorted. After the sort function, it is sorted, and then that sorted array is given to the plot function, which produces what you see on the screen. If the data are uniformly distributed, what do you expect this plot to look like? Just like this, yes. That's it. Yeah. In this case, we expect to find a linear fit from 0 ranging up to 1 with no curvature in that line. If we saw a whole bunch of values down here, we might see something like a little stretch to the right followed by this rise. That would mean we have a bunch of genes that are producing significant p-values. Sorry, you're really sensitive to that sound, I can tell. I'm sorry. Okay, so so again, we looked at this in histogram form. Now we've looked at it in linear form, and these two reinforce each other. Okay, great. Yes, sir.
Is it possible there are a lot of significant difference?
Yes. When you have data from cohorts that are wildly dissimilar, it is certainly possible to see a very large number of significant hits. So one of the things I learned when I was working in colon cancer research is that you shouldn't compare, say, cancers to healthies, right? So if you have lung tissue from a forever smoker and compare them to like a 20-year-old running athlete, you're going to have huge differences, because cancer is a tremendous dysregulator of expression. So a large number of differences will come from the cancer, and a large number of the differences will come from the disparity in age, and a large number of the differences will come from the distinction of looking at athletes versus people who are concerned about dying, right? So these are things that we have to be really careful about in lung cancer research. So one of the things that came up in the end was that we were trying to differentiate people who definitely do need to go for removal of a tumor of their lungs to one where people have a lung infection, like a kind of fungus that you can get in your lungs in the American Southwest. So in a case like that, you have something that's a clinically meaningful question that's driving the only difference between these cohorts. If they're not age matched, if they're not gender matched and sex matched and age matched and so on, you can mistakenly create biases where the differences are not specific to the condition you're actually testing for. Sorry, that was a long answer to a straightforward question, but having the only difference being the thing you actually care about in the study is valuable. Okay. So let's continue on down our sheet here. We would like, in this case, to look manually at the 100 lowest p-values. How many were in the total list? Like 1,000? So we're going to look at just the lowest 100. Again, we're using a compound function. We're still using sort on the p-values from the table. That's one of the arguments we're passing to the head function, but we're also passing it the number 100. Remember that head will typically show you the top 5 items. Here we've specified we want the top 100. Okay, so these values are showing just a few that have really, really low values. When you see something like 10e minus 09, that's to say you're going to scoot the decimal point over 9 times to the left in this case. So there's a lot of zeros in front of that 25056 that we see at the top left. All right, so just a few p-values that really stand out from everything else. Right. Now, I'm a big fan of the XKCD website. It has occasionally some really good mathematical insight that I think helps to explain why we do the things we do in science. So remember that we are doing generating p-values from a statistical test, and then we're going to perform multiple testing correction on them. This cartoon, I think, is one of the most insightful things I've ever read about it. So we start with a woman a person with long hair anyway, running into the lab shouting, "Jelly beans cause acne." Has anyone suffered from acne? Terrible stuff, right? So the person without long hair shouts, "Scientists, investigate!" Okay, so the scientists reply, "We found no link between jelly beans and acne. A p-value was greater than 0.05. Why do we use that? Tradition, more or less. Okay, that settles that. But then the person with long hair shouts, "I hear it's only a certain color of jelly beans that cause acne." Again, they shout, "Scientists!" All right, now we get to the meat of this cartoon. We found no link between purple jelly beans and acne. The p-value was greater than 0.05. We found no link between brown jelly beans and acne. The p-value was greater than 0.05. No link between pink jelly beans, blue jelly beans, teal jelly beans, salmon jelly beans. Anyone have a salmon jelly bean? Not happy. Okay. No link between red jelly beans and acne. No link between turquoise, magenta, yellow, gray, and tan jelly beans. Yeah, okay, it happens. We found no link between cyan jelly beans and acne. No link. Look at this one. This one's different. We found a link between green jelly beans and acne. The p-value was less than 0.05. The response, whoa. They continue. We found no link between mauve jelly beans, beige jelly beans, lilac, black, peach, orange jelly beans. But what's the part that people remember?
Green.
Green. Does this mean they've got a real finding that green jelly beans cause acne? They don't. How many tests did they perform here? 1, 2, 3, 4, 5. 1, 2, 3, 4. There are 20 different colors that were tested here. And they tested, do they have p-values below 0.05? So if you have a uniform distribution of p-values, how often do you randomly get a result below 0.05? Uniform distribution, so how often is the value below 0.05?
5 out of 100.
It's exactly 5 out of 100 or 1 in 20. So even if there's no effect, if you look for an effect 20 times, you expect to get one value below 0.05. So this is why you can't just use the 0.05 criterion when you've done something like gene expression, because here we've performed 1,000 p-values. Having generated that, we must be much more restrictive about what we accept as a real difference. Okay, so favorite cartoon ever, but let's now come back to the world of R. So there's a really good commentary here that I've given you. If you want to understand more about multiple testing correction, feel free to read some of these other pages. We're going to start with something called the Bonferroni correction. This came from, I believe, an Italian mathematician many, many years ago. But it's been incorporated in almost every stats package out there to create something called the Bonferroni correction for this. Now, Right. We're going to start by saying, did any of the p-values survive it when we used Bonferroni on this selection of p-values? Okay, so it receives the full list of p-values that we had, and then asks, essentially, how can I adjust these p-values to make sure we don't make even one mistake in claiming a difference where none exists? So having run all of those input p-values on this, we've now sorted the results that came back, and we see that this first value is 2.6 times 10 to the minus 6th power. Is that still significant? Is that still below 0.05? Yeah. So this is to say we need to move the decimal point left 6 places, which means we've got 5 zeros before the first 2. Okay, so that's good. The first, the lowest p-value initially did survive Bonferroni correction. How about the second one? Still below? Yes. You move the decimal place left 4 places this time. 1, 2, 3, 4. So you've got 0.0008. That's good news. Still below 0.05. Right. And now, how about this one? We're going to move the decimal point to the left 3 times. 1, 2, 3. 0.002. Getting a little closer to, like, say, 1% errors here. All right. So now we're going to scoot this one just 2 places. 0.03. You see how quickly we're creeping up towards this 0.05 arbitrary threshold. P-value correction by Bonferroni is very, very restrictive. Use Bonferroni when you want to make sure that none of the claims you make are false, right? So if you use Bonferroni, you are not controlling something in an aggregate FDR way. You're trying to avoid making any single mistakes. That's a very, very aggressive criterion. And when you've got this many p-values you're generating, you have a really good shot of throwing out some of the baby with the bathwater. That some of the things that really, people don't use that expression here. Oh. Kid. No, yes, when you throw out the bathwater, don't throw out the baby with it. Right. So, yes, in this case, you want to. Bonferroni is when any claim you make of a difference really, really, really needs to be real. In a lot of gene expression stuff, that is much too tough a criterion for us to reach. So we will talk about an alternative to that is much more popular in biotechnology. Let's try the more liberal Benjamini and Hochberg correction. Very frequently when we talk about false discovery rate, they're talking about Benjamini and Hochberg. So we're going to use the p-adjust function again, but this time we see that there is a difference, not just in the result, but in how we called the software. So both of these are making use of the p-adjust function. That's the built-in multiple testing correction feature of R. They're receiving the same arrays of p-values, but what differs is the method that we're selecting. Are Bonferroni and VH the only alternatives? No. If you put in $p.adjust, you'll get back feedback about what options are available to you. But these are really common ones, so I'm focusing on these. Now when we sort these, we see that the initial p-value is the same after correction. But then they differ in how these values have changed after them. So here we see that now we would move this left 4 places. So we got 3 zeros before the 4. Here we have 3 zeros before the 7, and so on. In this case, how many of these values are still significant, below 0.05? Is this one? Yes, because if we scoot this left 2, that's 0.043. It's below our 0.05 cutoff. But this last one isn't, because it would be only 0.07. Okay, so we have more survivors in this case when we do p-adjustment by Bonferroni, by Benjamini Hochberg, than when we use Bonferroni. I really like the fact that this is a bit about the sociology of science more than anything else. Bonferroni correction comes from the Italian mathematician, I think, who created it. Benjamin E. Hochberg, if I remember correctly, was actually discovered by a woman whose name is not Benjamin E. or Hochberg. But she thought, well, the idea I've come up with is actually based in ideas I combined from these two other people. And so she gave it their names, not her own. And it makes me realize again, dudes, we can be kind of arrogant. So anyway, it is okay to stand on the shoulders of giants and name the giants. Just a little side story about this. Now, why are these two giving rather different results? Bonferroni is about avoiding making any false claims, but Benjamin E. Hochberg is about limiting the rate of false claims. So in this case, we're essentially saying what is the worst aggregate error we can make. That we want no more than 5% of these claims of difference to be erroneous. That's a much lower standard of evidence than to say we want to make no false claims whatsoever. And that's where Benjamin E. Hochberg and Bonferroni really differ from each other. As a result, we very frequently see FDR-style metrics being used, the Benjamin E. Hochberg model, and relatively rarely see Bonferroni. But they each have their place, and it's important to remember they both exist. Okay. Now, in this case, the software used to create the transcript tables produced its own p-values and did the multiple testing correction on them. So if we look at the p-values they produced, this is what you see. So we didn't have to add this. We didn't have to do the multiple testing correction over again because it was already included in the table we're using. So yes,
slightly different.
It is slightly different. I would say, first off, Volcano was not limiting to just the named only gene lines. It was looking at all the transcripts. And they may be using one of the slight refinements on Benjamin E. Hochberg. So these numbers are not identical to what we see above. And I think that mostly reflects the fact that we've limited to just those with the gene symbols on them more so than anything else. Most typically, Benjamin E. Hochberg is just used very widely without modification. Okay. So we already have those values in here. I don't think that we need to make an additional correction beyond what they've already done. Now, I think I've talked about this link before, but if you're dealing with gene expression for the very first time, I wanted to note that there are many papers out there to guide you through why we do this type or that type of plotting. In this case, the interpretation of differential gene expression results of RNA-seq data helps to walk you through why people visualize things the way they do. Those are this paper. I gave the link in your notes, so in the script file, so that can be a useful reading. I believe this also covers the MA plots, if I remember correctly. So yeah, there's a lot of good stuff here. Why do we visualize things the way we visualize them is a good thing to know about. Okay. Now, what we remember is that the original input table from transcripts, I can show this, names, transcripts. It's got a capital T though, I think. Yeah. The original table has FC, fold change, but it doesn't have log base 2 fold change. I want to make sure we retain that because showing fold changes on a log scale makes much more sense. So we got to compute that. We're going to run this command, and it's going to create a new vector called log2 fold change by applying the log2 function to named only fold change. Are you required to use log base 2? No. Is there a function for every possible log you might do for log 3, for log 5? No. There is a simple log command, and you can see that you can pass it the base that you want to use. So if something other than log 2 is in is appropriate in your case, feel free to change that. Okay, but here we're going to do the log2 function and generate those values, dump them in a new vector. We also want to change the p-values. Okay, now why would we do this? I always sort of struggle with explaining this part, but in fact it makes perfect sense. So I will try to be really careful about it. If you were to look at the p-values as they are, you know that things very, very close to zero are what are going to interest us the most, right? These are the ones that are assuredly different from random, thereby meaning there's an effect of some sort, that they're different. However, if we look at p-values as they are, remember we made those histogram and sort plots to look at. It's kind of hard to tell from these big plots which values are really friggin' close to zero. So for that, we have some ways we can transform data that don't change their ranks. The lowest p-value is going to be the most extreme value when we transform it. But that really emphasize how very, very close things are to zero. And the negative log 10 formulation is a very good way to do that. So let me go ahead and run this function. All right, so sort named, I'm going to run ahead on the sort of named only p-val. And now I'm going to do a head sort neg log 10 p-vals. I have to remember how to do this. This is descending equals true. Oh, nope. It's decreasing. That's what they want. Decreasing equals true. Okay. Sorry, it took me a moment to remember the exact calling syntax here. These are the original p-values, right? We want these to be in the same order. This is the most extremely low p-value, this is the second most, this is the third most, etc. But we really want to emphasize, to punch forward those p-values that are way close to zero. So taking the negative log 10 of these p-values is going to do that for us. Here we see that this 2.505 times 10 to the minus 9th has been turned into a high value. 8.6 is the new negative log 10 of this p-value. The second p-value was 7.8 times 10 to the negative 7th. It has become 6.1 on this scale. So values that were very, very low before have become very, very high now. So you might be accustomed to thinking about very low p-values are what I care about, but very high negative log 10 p-values are what we care about. Good so far? Negative log 10 flips the scale and really punches forward those p-values that are lowest. Okay. Right. Now we've generated these two vectors, log2 fold change, negative log 10 p-values. As usual, we want them to be part of the table that we're going to use for visualization. So I'm going to cbind those on. We have the original table with just the lines with specified gene names. We have the log2 fold change that we've stuck on there, and we have this new negative log 10 p-values that we've stuck on there. When we look at the original named only table, we see it has these names. If we look at the extended table, we see that we've just glued on two more columns on top of that. Does everyone get that? Good. Okay, so we've just expanded, we've created what we might call derived fields. There's no information in log2 fold change that didn't already exist in the fold change category. And the information in negative log 10 p-values is derived from the p-values, but no, it's not adding information, but it's making it easier for us to plot, in effect. So we've now built the big data structure. Now, because it's me, we're going to do a plot in base R. This is a very simple-minded way to go, but useful just the same. The plot function is just built into R. You don't have to have ggplot or anything to do it, and you don't have to remember the syntax of how to do it either. You can simply say I want log 2 fold change on the x-axis, and I want negative log 10 p-values on the y-axis. And over here, dutifully, the software kicks out a new plot for you. Let me do this there we go. Okay, now remember, our emphasis has changed from being very close to 0 on p-values to being high on negative log 10 p-values. So these values that used to be really, really big and close to 0 are now showing up way high on this graph. And beneficially, we changed our fold changes from linear scale to log base 2 scale. They should be centered right around 0 here. And we have some values that are to the left and some values that are to the right. And those reflect, is this gene up in dudes or is it up in women? So that kind of shifting left and right is going to tell us about which cohort favors each of these genes. Right. So, as usual, we would like to add a bit of annotation to these graphs to make it easier to interpret. We're going to throw 3 lines on top of this. Okay. This produces the classic structure of a volcano plot. We've now subdivided the graphing space into 6 boxes. Anytime you see one of these plots, you should be thinking about how these boxes relate to each other. First off, we put in a horizontal line at the negative log 10 of 0.05. That is this line right here. I've actually kind of committed a sin here to make the data look pretty. I apologize. But I'm showing p-values rather than the q-values that they computed for us. This should probably have been q-values. I didn't update the script though. Okay. So here, these are p-values that are below 0.05 appear above this line. P-values that were higher than 0.05 fall below this line. So already your attention should be going to, okay, these are hits. Things below this are non-hits. We also have 2 vertical lines though. This one represents higher in, oh gosh, I should know this one, higher in females. So anything to the left of this line, oh, I'm still scratching it. Anything to the left of this line is higher in, say, females, and then anything to the right of the other line would be higher in males instead. So a statistician would probably say, why are you even bothering with having the left and right lines on here? Because what you should care about is if it's a significant difference or not, not is it at least 2-fold change higher or lower. But biologists always helpfully sketch those lines right back in again and say, if it makes a difference of only 10% expression, I don't care. So ultimately, these 2 lines have remained in common usage for interpreting volcano plots. Okay, so if I were to make an obvious draw of conclusion here, I would say people don't care about the stuff in the lower middle. Why do they not care about it? Because it doesn't have a significant p-value and it doesn't show a major fold change. People don't care about stuff to the lower left. Yes, it's got a big fold change, but it's so noisy it doesn't give a significant p-value. For the same reason, people don't care about the stuff at the right. People also don't care about the stuff that shows up in the middle top. Yes, the p-values are significant, so the statisticians get excited, but biologists don't care because it's 10% up or 10% down. Who cares? So this and this, the upper left and the upper right, are the golden zones. Those are the things that people actually care about because they have statistical significance by being up high, and they have a big enough fold change that they are considered biologically meaningful. So one of these is a statistical definition, the other is a biological definition. Great. So that is our base R implementation of a volcano plot. Be nicer, couldn't it? GG. GG plot to the rescue. Yes, sir. So now we have some ways to look at these data. So let's start with what is the lowest log 2 fold change that we see. Here I'm using the min function. Min stands for minimum. There's also a max function, so you can see what is the highest. So here we have a lowest log 2 fold change of negative 7.44. What does that number mean? What does that number mean? Negative 7.44 on log 2 fold change. Does that mean that the protein is, that these genes are expressed 7.44 times as much? Oh, I was really hoping to see a big head shake on that one. Is this gene expressed 7.44 times as much in one cohort as in the other? No. Because it's a log base 2 fold change. So in order to translate this back to a ratio, we have to raise 2 to the value of 7.44. Well, how do you express that in R? Helpfully, it has exponentiation functions built in. That little hat character means raised to the power of. So when you see 2 caret minimum log 2 fold change, you are converting back to a linear fold change. That's one of the values of using log base 2, because 2 is easy to type. When you want to return it to linear scale, you can do that very readily. However, that value is actually a little hard to understand because it's 0.005. I mean, that you kind of like the big part of the ratio on top. Did I do that as the next step? I did. Look at that. Okay, so we're going to take the reciprocal of that in order to flip the fraction. There we go. Now we see that if we compare the intensity of this transcript from one cohort to the other, we have a 174 to 1 ratio. That's pretty extreme, isn't it? So if something's really close to that, the line of 1 up or 1 down in log 2 fold change, it's just a 2-fold change. But as you get way out to the edges of the volcano plot, you're looking at some pretty extreme fold changes from one to the other. This may in fact be a case where the software has used imputation to fill in a bunch of zeros on one side, and that gave us this very large fold change of 174-fold. Okay, right. Now we're going to do the same plot, this time in ggplot2. All right, I'm going to just grab that whole section out. I think that this example is nice for showing ggplot's ability to add layer upon layer to the same plot. You often see this used to describe the progressive, almost iterative way in which we build up scientific graphs. We started with our input data, specifying log 2 fold changes on the x-axis, negative log 10 p-values are on the y. We then specified to fill up that space with our data points, each using just a scatter plot strategy. We decided that we needed to add geoms representing the 2 vertical lines at x-intercept 1 and x-intercept -1. We still throw in our crossbar, our horizontal line. Its y-intercept is the negative log 10 of 0.05. There's our significance line. And we are also going to add a title to it called Volcano Plot. Very imaginative. That's great. But what do you notice about what's on screen? I just ran the ggplot command. Where's my plot? That's still the old base R thing. When you create a plot in ggplot, it doesn't immediately show it to you. You might end up just storing it. So let's see. Hold on, is that the... I think I botched this. No, it is actually showing it. I'm sorry. Let me repeat the command, this time without that one on there, and then I'll know that I'm looking at the ggplot version. Oh, it is. Okay. Yes, so this is the ggplot version. If I want to save this out to a file, I can still use ggsave and all of that stuff. Now, I had a couple questions written here. Okay, yes, this is the part where I talk about the 6 regions of the volcano plot. We've already done that, so that's covered. If you find you're forgetting which one is which, feel free to just read that section again. You have the script with you, so you can always look back on your notes there. Okay. Now, I've got this note in here. Remember that we plotted negative log 10s of p-value rather than using the q values. And we might have some worries about how that's affecting the plot. Ideally, if you're going to make this for publication, it's a really good idea to incorporate multiple testing correction in your plot. Sometimes it doesn't look as Volcano-like when you do that, and that's one of the reasons I chose not to do it. So if I were to change that, I would probably come up here to this negative log 10 p-values thing here. I'm going to copy this line, and this time I'm going to make it the negative log 10 q-vals. Oops, I really mistyped there. Q-values. And here I'm going to grab out the q-val column. Where's the mouse? Sorry? Well, yeah, you can name it whatever you like. Oh, sheesh. I'm just typing all over the place. Okay, does that look right? Okay, I'll grab that out. So if I plot the Q values instead, oh, come on, Mr. Mouse, work with me. All right, I still need to glom that together. So I'm going to just make a table that has both neg, log, 10, Q vals. So now that will be built into the extended table. And so now when I come back down here to ggplot, I can specify that on the y-axis, we're going to use the Q values instead. Okay, now I can simply blast that back out, and now I have Q values. Do you see what I mean about the plot changing quite a lot away from the volcano shape? We still have our significant hits showing up above the line. The number of dots appearing above that line has changed a lot, because once you use multiple testing correction, you're being much more restrictive about what you can call a significant difference. So 1, 2, 3, 4, and 5 right on the line are the number of genes that we can potentially call differential after multiple testing correction has been applied. Okay. So we've already talked about using ggsave to produce PNGs, PDFs, and so on. One of the questions that someone raised yesterday, I think, was, what if I have some tweaking I want to do? Maybe I want to alter the language that I use to put a title on the graph because it's going to go into a paper. And here you can see I use log 2 fold change as the name here and neg log 10 q-vals here. It's not beautifully named. So how would I go about altering that text? Well, yes, you can just fix it in your R code so it renders to exactly what you want it to be. But if what you're doing is something a little more selective, maybe you really want to draw attention to points 1, 2, 3, 4, and 5 here. The easy thing to do would be to pop this into Illustrator, for that matter, and just change the color of those dots. This is not hard to do, but if you have it as a PNG, it's a bitmap, not an editable drawing that you can deal with in Inkscape or Illustrator. It is possible in ggsave to save stuff as an SVG. Has anyone heard of this graphics format? Okay, great. So SVG is something that you can export directly from R's ggplot library. If you do that, then you can edit this to your heart's content. Now, does that mean that this data point, which is one you don't really like very much, you can erase? No. You should not do that. You definitely should not do that. But it is possible to do, but you shouldn't. Yes. When we look back at the notebooks for Maxwell's oil drop experiments, you'll see that sometimes when he was evaluating the drops that he was using, he would write "good one" beside these, or looks squirrely. So yeah, sometimes scientists really have edited their data until they got the result they liked. But we should not do that. You should show the data as they are, and that is valuable. Okay. We've reached the end of the demonstration, I think. There was no more text in the script. Just saving it, I think. Yeah. And we've gone through the exercise of editing the editing the Volcano plot code to show Q values rather than P values, and that all worked. So that's great news. Who here feels that R is something that can help you in your research? Good, a few people. Who here would prefer never seeing a programming language again? Okay, I understand this. You know, I have been programming in one language or another since I was 8, and for me, it is a natural environment in which to try out new ideas. It's not going to be true for everyone. I will say, knowing a bit of R can go a very, very long way towards saving time for you. I haven't even shown you useful things like how to merge tables. Just as a simple example, if I've got a bunch of p-values and q-values and fold changes for a bunch of genes, and I want to add description data to them, but that's not in the original table, it's in this other table, there's a function called merge in R that lets you grab out particular information from this table that has the same gene name in both tables. Merge will do that in one-liner for you. So instead of spending all day control finding in a text document, you can just have R do the work for you. This has really been focused on how can we get gene expression data into common imaging formats for gene expression data. It's not a complete introduction to R, but at least I hope it gives you the basics for when you have a problem that you think could be solved this way, you can get your answer pretty quickly. Okay, I want to thank you very much for staying with me these 4 days. It's been a lot of fun for me, and I hope you've had fun too. I will try to get these videos of the screen recordings from R, and of course the most of the lecture videos to you as quickly as I can. And I hope I get to come here again because Crete is an amazing place. Thank you so much for sharing your island with me. All right.